Okay, so if you're looking at the exams, what are y'all on right now, Mohammed?
Chapter 2.
You're on chapter 2, okay. Oh, but that's different for y'all. It's like forces and fields, right? Or is that? We're on voltage, potential, energy, capacitance. Yeah, so if you're looking at exam, oh, that's physics 101. Hold on, I'm sorry. You'll have capacitor circuits on the quiz. Like this right here. We're going to get into this next week. And these things, like all this stuff, anything with capacitors. So you'll have the last part of chapter of exam 1 and the first part of exam 2. Okay, usually exam 1 includes like half of chapter 2, the voltage, potential energy sections. Okay, let's sort of step through the ideas that we had. Had this idea, first of all, that just potential, V, is equal to a potential energy per charge. And of course, I'll ask you a question, what is potential? I think I asked a similar thing about fields. What is fields? That it's a force per unit charge at its very base level. And so potential is a measure of energy per charge. And so there's a lot that we can do with that. For example, we can say that the energy of a particle is equal to Q times delta V. We did that in class today, actually, where if I have a particle that, or was it today? Say I have some equal potential lines like this, say this is 10 volts, and I have another equal potential line like this, say this is 12 volts. Then as I have a particle that goes in this direction, it has a delta V equal to 2 volts, and it's going to gain energy when it does that. Okay, and so my particle, say it was a 2 coulomb charge, would gain an energy of 2 coulombs times 2 volts would be 4 joules of energy. And then we talked about in that first, this was before our exam, right? Because we did chapter 2 at the beginning before we did our exam. I can take this energy that my particle now has, and I can figure out what the speed of that particle is. And so I can say that that 4 joules is equal to my kinetic energy, which is 1/2 mv squared, and I can solve for v. I can figure out the velocity of that particle now just by saying, okay, I have this charged particle that's moving from 10 volts to 12 volts. This is an equal potential line. The red line is 10 volts. The blue line is 12 volts. And as I move from this point to this point, that's a difference of 2 volts in potential. When I do that, my particle will gain or lose energy. It'll gain energy when it moves from one line to the next as I move from this potential. It's just like a particle moving in the gravitational field, that if I have a particle that moves from here to here, it now has more or less energy, kinetic or potential. And then if I have a particle that moves from there to there, likewise, it can figure out what its kinetic energy is. We did that last semester in the chapter on work and energy. I'll pull up some questions about that, but let me sort of do other big ideas. We had something else come up that might be a different way that we would look at this. This equation is on your equation sheet, but the change in potential energy, I'm saying potential energy, but we can talk about this in terms of kinetic energy too, is equal to the work that you do, F times D. And that work is equal to Q times the electric field. F is equal to Q times E, and then times D will give us our change in energy. So just like we did before, where I have a particle that's moving along equal potential lines or between equal potential lines, if I have an electric field, say like this, say my electric field is 2 volts per meter. Remember, electric field can be measured in newtons per coulomb or in volts per meter. Those are the same units. So if I have an electric field of 2 volts per meter, then I can calculate what is the work done. Say if I have a particle a 2 coulomb charge that moves in this direction, then I can figure out how much energy it's gained after it moves across a certain distance. Or let's say it moves across a distance of 3 meters, then I can say, okay, this 2 coulomb charge going across 2 volts per meter over a distance of 3 meters will now have an energy of 12 joules. You're probably going to have a question something like that, either a particle moving between 2 equal potential lines, and I ask you what is its velocity, or you'll have one where you have a particle that's moving along a field line like this, and you have to figure out what is its velocity. These are the same questions, really. You just approach them differently. So if I were to draw my equal potential lines, they would be there and there. So this particle, as it moves over those 3 meters, is really just moving across between equal potential lines. Let me step back, and I'm going to review both of those, okay, what we did on both of these, because they're very, very similar. Imagine here, if I were to draw my field lines would look like that. And so I have a particle that's moving from here to here across a potential difference of 2 volts. And I got the 2 volts, 12 minus 10 is 2 volts. I'll begin with my basic understanding of potential, which is energy per charge. And then I can get an expression for potential energy. Or we can just think of it in terms of energy, right? It'll be potential or kinetic, depending on which direction the particle is moving. So like with gravitational field, if I move a particle from here to here, it gains potential energy. But if I move it from here to there, then it gains kinetic energy. So we can sort of think about those things interchangeably. It's just, is it moving or is it gaining potential? By the way, this equation right here is on your equation sheet. So then I can figure out its energy just by saying, okay, I have a 2 coulomb charge moving across 2 volts. I had to figure that out by looking at the potential lines. And that gives me 4 joules. And then now that I know the energy, I can set that equal to the kinetic energy formula. That 1/2 mv squared is not on your equation sheet for second semester. So make sure you know this. The second one is similar, very, very similar. My change in potential is force times distance. The force is QE times V. By the way, I think this is on your equation sheet too. Y'all might want to check that. I'm pretty sure it is, or something similar to it. And here, I don't know my change in potentials. I just know the distance that I'm covering through my electric field. So as I move from here to here across a distance of 3 meters within this electric field, I can figure out how much energy it's gained. Do you have that equation sheet?
Yeah, it's just delta x instead of distance.
Okay, well that's the same then.
For some reason, the q's negative.
Oh, yeah, don't worry about the negative. It sort of has to do with that, am I gaining potential or kinetic energy? In your questions, it'll just be gaining kinetic energy. I would expect a free response. We'll look at some. Let's look in the old test. We'll look and see if we can find one similar to that. Mohammed?
Would it be negative? Let's gain potential energy.
Let's see. Yeah, the potential energy is that right? The potential energy is the negative of QEX. I always get it. I have to think about it, Mohammed. Don't worry about the negative, though. It's not that important. It is important, but it's not important for this right now. Let's look at an exam 1. Okay, like number 4 here. Yeah, it looks like this was a free response last year. I have a proton that moves from a potential of 8 volts to a place where the potential is negative 2 volts, and I just want to know the speed of the proton. This is exam 1 from last spring. So the first thing I need to do is figure out what is my delta V. I'm going from 8 volts to minus 2 volts. So my delta V is going to be minus 2 minus 8, or minus 10 volts. We're just going to sort of forget about the sign. The sign isn't terribly important right now. And then I want to know the speed of the proton. I want you to remember, y'all. Let's just take a little side. So when I'm moving from high to low, my electric field's running this way, right? So a proton, if I let go of a proton right there, a proton will always tend to move from high to low potential, whereas an electron will always move from low to high. And so this guy is moving from an equal potential line that is at 8 volts to an equal potential line that is at -2 volts. So it's moving in the direction that it should, and so it's going to be gaining kinetic energy. And this is where that negative is going to come in. It's going to give you a positive value for the energy. Anyway, the signs aren't that important. In fact, I'm just going to get rid of it. I'm going to say that my change in potential is 10 volts. And now I want to know the speed of the proton. Well, I know that my potential energy, or I'm just going to say kinetic energy, is equal to Q times delta V, which is going to be 1.6 times 10 to the minus 19. I know that because it's a proton. I know both its charge and its mass, times delta V, which is 10. And so that gives me 1.6 times 10 to the minus 18 joules. Now that I know its energy, I can set that equal to 1/2 mv squared. 1/2 mv squared, where m is the mass of a proton. It's 1.67 times 10 to the minus 27. That's on your equation sheet. It's in the upper left-hand corner with those constants. It's the mass of a proton times v squared. And then you would solve this for v, and whatever it is. Something big. Okay? I would expect a problem like that, probably on the quiz, on the test, as a free response, something similar to this. Y'all do free response in your class? Yeah, good. Okay. You're good on that for now? Or is it good? It's good to review that. It's important. Oh yeah, we cool. Okay. Practice. It'll take practice for it to really sink in. Some other things that you're going to have to do is you're going to have to find the potential due to a configuration of charges. Let's see. Well, did I have to do it here? Maybe I did it here. Okay, yeah, so it was on free response. I wanted you to find the potential at point A due to these charges. So right here, I want to know what the potential is. This is a lot easier than finding the field because you have to deal with vectors. All you say is the potential is the sum of the individual potentials. And so that's going to be V1 plus V2. V1, which is due to this charge, is going to be 9 times 10 to the 9th times 9 times 10 to the minus 9. That's the charge right here. That nanocoulombs is minus 9, divided by the distance, which is 3 meters, plus 9 times 10 to the 9th. 25 times 10 to the minus 9. And check it out. I have to put a negative right there. Anytime you're dealing with scalar quantities, you have to include the sign. So I included the negative right here. You can tell that on your equation sheet because that equation doesn't have the absolute value bars like the electric field and the force equations did. Divided by the distance, KQ over R. The distance here, that's a 3, 4, 5 triangle, so that's 5 meters. I just did the square root of 3 squared plus 4 squared. Numbers work out easily here. These cancel. That gives me a 3 right here. This gives me a 5. Those cancel. So I've got 27 minus 45. So what's that? 18 minus 18 volts. Okay, that's the potential at that point. It's not a potential difference. The potential difference would be if I asked you, hey, what's the potential up here and the potential down here, and what's the difference between them? This is just the potential. So remember we're talking about potential. We have three different terms that float around. Potential is the energy per charge at a particular point in space, and that's what we were doing here. And then potential difference is the difference between 2 points in space. And we were doing that earlier, where if we had an equal potential line here and an equal potential line here, delta V is the difference in those two equal potential lines. And then later when we get into circuits, we talk about voltage. And voltage is the same as, do you remember what it's the same as? Voltage is the same as potential or potential difference? It's okay if you don't remember. It's potential difference. So when we talk about voltage, that's potential difference. It's the potential between two different points in the circuit. So that's something you're going to have to do, is you're going to have to figure out the voltage of a configuration of charges. And you have to do that on the quiz and the exam. All right, can I clear this, y'all? You want to look a little bit at circuits? We started them past couple days. Oh, good. Well, we're not quite to resistor circuits. We're just on capacitor circuits. Let me find some simple ones. Are y'all pretty far along in capacitors? Oh, okay. We're not. We just started them today, really. Now, these aren't simple. You find. Let's do. I'll just make up one. So the hardest of the capacitor circuits, if it's just a either series or parallel, is the series. So let's do one of those. I want to remind you what the rules are for capacitors in series. These are going to be really important as you move forward. First, they have the same charge. Second, the equivalent capacitance is equal to, oh, this is the one where it's 1 over, right? That's how you find the equivalent capacitance. Any set of 2 or more capacitors in series, you can replace with a single capacitor. And that'll become a really important step when we move into complex circuits, combination circuits, where they have both series and parallel. Third is that the voltage, the total voltage, is equal to the sum of the individual voltages. I'll show you what I mean. And then fourth is that Q is equal to CV, which is sort of our own law for capacitors. So let's imagine this circuit. Let's say I have 12 volts. And let's do it easy right now. Let's say that this is 3 microfarads, 3 microfarads, and 3 microfarads. You're going to find that most of the circuits that I give you, you don't even have to really put your pencil to the paper, at least not with any numbers. That you'll find that it'll be really useful for you to draw out more simpler circuits, but that you won't have to really put any numbers to it because the voltages or the charges will divide up evenly or in some predictable way. So here, think about what is the voltage on each or on the leftmost 3 microfarad capacitor. Any inkling about how you might figure out what that voltage is just by looking at this? And I want you to think about these rules over here. Have the same charge. This is the equivalent. This is the total voltage equals the sum of the voltages, and Q equals CV. Can you think about what is the voltage on the leftmost capacitor? Or can you give me maybe a guess for what that voltage is? How do the capacitors compare to one another?
They're all the same.
They're all the same, right. And I also know that capacitors all have the same charge. So all these capacitors have the same charge and the same capacitance. So what can I say about the voltage?
Voltage is equal to the sum.
Okay, yeah, the voltage is equal to the sum. But what I'm saying too is that all of these capacitors have the same charge because they're in series, and they have the same capacitance just because they're all equal to 3. And so if those two are the same, how will V compare for each of the 3 capacitors? Well, V is going to be all the same because V is Q over C. And so if they all have the same Q, they all have the same C, then these are all going to have the same voltage. Excuse me. So what is the voltage then? It's going to be 4. Awesome. 4 volts, 4 volts, 4 volts. Okay? So all 3 of these capacitors have the same voltage of 4 volts. That's only true because they're in series and they're all the same. Okay? And then I could go back and figure out the charge on each of them. The charge, which is going to be C times V, will be 3 times 4, or 12 microcoulombs, 12 microcoulombs, and 12 microcoulombs. So that problem is pretty simple. I don't have to create an equivalent capacitance or anything. I can just do it that way. Let me show you a different way to do it. So if I started with the same circuit, and I didn't make those arguments about, well, these are all the same capacitors, and so they have to all have the same charge and the same voltage. Sort of the more rigorous way to do this is like this. The first step I would do is find the equivalent capacitance. And the equivalent capacitance is 1 over 3 plus 1 over 3 plus 1 over 3. That's equal to 1. Okay? So to find the equivalent capacitance, so I could redraw this circuit, and I find that it's usually helpful to redraw the circuits. So this is 1 microfarad and 12 volts. Then, second is find Q equivalent. That means the charge on the equivalent capacitor. Q equivalent is equal to C equivalent times V, which is going to be 1 microfarad times 12 volts, which is equal to 12 microcoulombs. So this has a charge of 12 microcoulombs, but I know for capacitors in series, they have the same charge, and they have the same charge as the equivalent capacitor. So if I have 12 microcoulombs on that capacitor, on the 1 microfarad, what do I have on this one? I have 12, 12, and 12. Students sometimes make the mistake because they get them mixed up with resistance that this would be 4, 4, and 4. But that's not true. It doesn't split up the charge. It shares the same charge. So I'd have 12 microcoulombs, 12 microcoulombs, and 12 microcoulombs. And then I can go back and I can figure out what is the voltage on each of them. The voltage, so that'll be step 3. Find the voltage on each individual, and that's going to be, let's say Q is equal to CV, so V is equal to Q divided by C. So that's 12 divided by 3 is going to be 4 volts, 4 volts, and 4 volts. These 3 steps are for caps and series. You need to master that before we move on into combination circuits. Let's do a caps in parallel too. Caps in parallel are a lot easier. Let me show you why. First of all, let's write the rules for caps in parallel. What do they have? They have the same voltage. Caps in series have the same charge. Caps in parallel have the same voltage. 2, the equivalent, equals C1 plus C2 plus C3. The third rule, I'm going to write them in parallel. I'm going to skip 3 and just go down here and write 4. Q is equal to CV. And then later I'll come back and I'll show you what rule 3 is. Although rule 3, as I told you in class, rule 3 is not real useful, so I don't usually give it. Okay, so let's do a capacitors in parallel. Let's say this is 3 microfarads. Let's say this is 2 microfarads. And this is 12 volts. If I want to know the charge and the capacitance, the charge and voltage on each of these, this is pretty easy. In fact, I don't even really need to write the steps down. But if I was, I would say, well, first, I know the voltage. Voltage is same as battery, or same as the source, I'll call it. In this case, that's the battery. But later when we do combination circuits, it'll be whatever voltage is across that particular section. We'll see those in class soon. What's my voltage then across the 3 microfarad? Let me remind you, Q is equal to CV. So V is equal to Q divided by C. What's the voltage across the 3 I'm sorry. Never mind. No. Forget I said that. What is the voltage across the 3 microfarad? NV12, yeah. Sorry, I don't know what I was thinking. And then across the 2 is 12. And now that I know the voltage and the capacitance on those capacitors, I can find the charge. Q is equal to CV, and so that's going to be 3 times 12, or 36 microcoulombs. And then this is 24 microcoulombs. And so that's the charge. Let's go through the steps here and just figure out what is the equivalent capacitance. Because I'll probably give you a question just asking, what is the equivalent capacitance of this circuit? So you're sort of done with that circuit. But let's imagine, what if I wanted to know the equivalent capacitance? I would say that's 3 plus 2. And that's 5 microfarads. Take a little aside. I'm going to show you that third missing rule, which, as I said, is not very useful. If I want to figure out the charge on this new equivalent capacitance of 5 microfarads, 12 volts, that charge would be equal to CV. 5 times 12 is 60 microcoulombs. So the charge on this equivalent capacitor, which isn't a real capacitor, it's just sort of an intermediate step. It's not in the actual circuit. I mean, I can use it in my diagram to replace these 2 capacitors. You'll see why that's important later. It is kind of important. I want you to notice that 60, or rather 36 plus 24 is equal to 60. The 36 that I had here and the 24 that I had here, that is equal to 60. So if I wanted to write another rule, I could say that Q total is equal to Q1 plus Q2. Like if I wanted to keep them all in parallel, I write it in that sort of hard to see yellow because it's not very useful to remember. Okay? You want to look at a more complicated circuit from one of the old tests, get a preview of what we're going to do in class. Is that okay? Okay, cool. You'll stop me if you feel lost. Are you feeling lost? It's okay if you are. Feeling lost? You haven't gotten to them yet. Okay, these are new. We're going to be doing them in class. So seeing them here, I think, will help you some. Let's look at this one. It's a good sort of circuit. I want you to notice that I have different parts in this circuit. I have something right here that is in series. I have 2 4 microfarads that are in series, and those appear to be in parallel. I can tell it's in parallel because I got these 2 junctions where they split into 2 pieces. And so I have these 2 4 microfarad capacitors that are in parallel with this one. And then all of this stuff right here is in parallel or series with the 4 microfarad. Yes! You're amazing. People often miss that, and the reason is like they see the corner and they think that it's in parallel, but it's not. That the 4 microfarad right here is in series with this whole thing right here. So the hard way to do this would be to simplify it completely. So let's do it the hard way, and then later you'll be able to see a simpler way. So I'm going to simplify this whole circuit, and just break it down so that I have one capacitor and one battery. And the way I do that is I sort of start on the inside and work my way out. These two capacitors, the equivalent, is equal to 1 over 1 over 4 plus 1 over 4. That's equal to 2. Remember I told you in class there are particular numbers that I like because they give you nice round numbers? That's one of them. I like to do 2 4s in series just because it makes the numbers easy to work with. And if I redraw this circuit, it looks like this. I have a 4 microfarad, I have a 2 microfarad, and another 2 microfarad. The next thing that I'm going to do is I'm going to look at these two capacitors. Those two are in parallel, and if I redraw them, they're going to have an equivalent capacitance of 2 plus 2 equals to 4 microfarads. Because I know the equivalent capacitance for capacitors in parallel is just the sum of the individual capacitors. And so this is going to be 4 microfarads, 4 microfarads, and I'm done, almost. Those 4 microfarads are in series or parallel? Series, right, because there's no junctions. So if I want to find the equivalent capacitance, which that might be a question, it probably will be a question, I would do the 1 over 1 over 4 plus 1 over 4, and this would be 2 microfarads, 12 volts. Now that I have that, I can begin stepping back and thinking about what are my voltages and my charges. But let's first just look at this and think about what is the thing that I'm looking for. I'm looking for the voltage across this left 4 microfarad capacitor. What's the voltage across this 2 microfarad capacitor right here? It's just 12 volts. I have 12 volts across one capacitor. What about right here? What's the voltage across these two 4 microfarad capacitors?
It would be double that.
Not double, but you're thinking along the right lines. Each would be half that voltage.
6.
Yeah, because I know that these have to add up equal to 12. So I know then that this is 6 volts and this is 6 volts. Now I want you to recognize that this 4 microfarad capacitor is replacing these two 2 microfarad capacitors. So if I have 6 volts, this is tricky, I have this 6 volts here, how does that go across these two 2 microfarad capacitors in parallel? What's going to be the voltage across these two 2 microfarad capacitors?
3 volts.
You'd think it would be 3, right? Because I have 6 volts, and you'd think that it would split it up. But remember, capacitors in parallel don't split voltages. They share voltages. It'd be 6, right. So I'm glad you said that, because now you'll never forget. So this would be 6 volts and 6 volts. Now I want you to recognize, look at this. It's going to blow your mind. This 2 microfarad capacitor was the equivalent for these two 4 microfarad capacitors. So if I have 6 volts across that 2 microfarad capacitor, which is the equivalent of the 2 4 in series, what's the voltage across the 4 microfarad capacitors? Is it 12 or 3 or 6?
12.
Where did you get that extra energy? Like you're telling me that I have 6 volts across a 2 microfarad capacitor, and now I'm going to have 12 volts across 2 capacitors. You're getting a lot more energy. And not 6 either. Remember, for capacitors in series, V is equal to V1 plus V2. It'd be 3, right? So my V would be 6. That's my source voltage. We told it like it was a battery before. And then V1 and V2, because they're identical capacitors, they would both be 3 volts. I know that you didn't see that, but soon, in the next week or two, before the next exam, you'll be able to look at a circuit like that, and in a couple of simple steps, you'll be able to tell me the voltage on every capacitor. just because you'll begin to see how those voltages are apportioned in either series or parallel. Trust me, it seems really foreign now, but in a couple of weeks you'll be a pro at it. Okay? Trust me? Okay, good. Good. I'm glad to hear that. Okay, let's do one more and we'll wrap it up unless you have a particular questions. Particular questions or concerns? All right, I'm going to clear this. Oh, let's see. That's all. No, that was too complicated right now. Let's look at another old exam. This is spring 18. Okay, let's do number 4 and 5. I want to know the equivalent capacitance of this circuit. No way, man, that's just like the one I did. Oh, let's find another one. Let's go to spring 17. Okay, let's do this one, number 4 and 5. What is the equivalent capacitance of this circuit? This is spring 17, number 4. What is the equivalent capacitance? And then the next question, what is the voltage across the 6 microfarad capacitor? Okay, so look, 3 threes in series. I'm going to start up here at the top. Let's just talk through it, and then I'll write it down. 3 threes in series, what is that? We did that earlier. No, not 6. 3 threes in series, that's 1 over 3 plus 1 over 3 plus 1 over 3.
It's 1.
It's 1, right. Don't worry, I use just a handful of common numbers, and so pretty soon you'll just see them and you'll say, oh, that's equal to 1 microfarad, because it's 1 over 3 plus 1 over 3 plus 1 over 3, and that's equal to 1. I do that 1 over business because it's in series, and that's our equivalent capacitance. I can redraw this. I find that it's, especially as you're practicing, it's really useful to redraw the circuit at every step. So I have 1 microfarad, 2 microfarads, and 6 microfarads. What do I do next? Maybe the 2 and the 6, the 1 and the 6, the 1 and the 2. What do I do next? The 2 and what?
The 1.
The 2 and the 1. I do the 2 and the 1 because these are in parallel with one another. But the 6 and the 2, for example, are not in series with one another because there's a junction between them. And so these aren't in series. All right? The 2 is in parallel first with the 1, and then that whole thing will be in series with the 6. And a 2 and 1 in series is equal to 3 microfarads. So if I redraw this again, I get a 6 and a 3. And we know what a 6 and 3 in series is. You all know? See, that's 1 6 plus 2 6 is 3 6, which is a half, so that's equal to 2. So the equivalent is equal to 2 microfarads. So that's B. Again, soon you'll be able to just look at this and you'll say, oh, this is 1, 1 plus 2 is 3, 3 and 6 in series is 2. You'll be able to look at that and just tell it really quickly. So a question like this you'd be able to do in just 20 seconds maybe. But for now, write down all the intermediate steps. That'll help you learn it more rigorously. Now the next question is, what is the voltage across the 6 microfarad capacitor? So I want to know the voltage across this capacitor. In fact, I could ask the voltage across any one of the capacitors. Okay, this is fun. So I have 12 volts here. That means I have 12 volts here. I have 12 volts here. But I know these two capacitors are going to split up that 12 volts because they're in series. They don't have both have 12 volts because they're not in parallel. They're in series. So I know that the voltage across those two capacitors will add up to equal to 12. I know that it's not going to be 6 and 6. How do I know that? They're what?
They're not parallel. There's more there's 3 and 6.
Right, they're different, right? So I know that they're not identical voltages. So this is going to be a voltage that's different from this one. Do y'all remember, not you, Mohammed, but the other, Leah, Logan, in class today, I said that if the capacitance is big, the voltage is small, and vice versa. So big capacitors have small voltages, and small capacitors have big voltages. It's inversely related. We'll see something similar but opposite for resistors. But for now, big capacitors, small voltages, small capacitors, big voltages. So which one of these is going to have the bigger voltage? The 3. So I'm going to write up here big voltage, small voltage. Okay. I also know that these two voltages have to add up to equal to 12. The big voltage and the small voltage have to add up to equal to 12. By how much bigger is the voltage across the 3 microfarad going to be over the 6 microfarad? By what factor is it going to be bigger?
2.
By a factor of 2. So the voltage for the 3 microfarad is going to be twice the voltage for the 6 microfarad. Can you think of 2 numbers, one twice that of the other, that add up equal to 12? 2 numbers, one twice that of the other, that add up equal to 12. 8 and 4. So that's my answer. So I have 8 volts here and 4 volts here. You might say, gosh, I would never think of that on the test, but you will. And in fact, I use 12 a lot, and I use factors of 2 a lot, so you'll remember those numbers too. Okay? I think that's the answer, right? Oh yeah, that is the answer, because we wanted to know this voltage, and I now know that it's 4 volts. Let's go ahead and wrap it up, though. I can figure out the other voltages. The 2 microfarad capacitor, what's going to be its voltage?
The same as 3 microfarad.
Yes, you're amazing. 8 volts. You would make me so happy if you told me the voltage on the 3 microfarad capacitor.
That's because they're in parallel. Or
Yeah, so this is the equivalent capacitor, which has 8 volts. That means that this has 8 volts, and all combined, these are also going to have 8 volts. What's the voltage across one of the 3 microfarad capacitors?
8 divided by 3.
Yes. All of them have 8/3 volts. Okay. There is a more difficult way to do this. I can show you that in class, but it was, I think it's a good point to stop right there. It sort of looks like a bunch of gobbledygook at first, but it begins to make sense. The rules aren't that complicated. The rules are pretty simple. There's kind of a lot of rules, but once you get them all figured out in your head and sorted, it becomes, I think it's kind of fun to work through circuits. This is one of the more difficult circuits. There'll be sort of one step up from this that we'll do for the free response. And we'll do that in class, and we'll do it next week during the help session. Okay? Is that cool for today? All right. I'm excited about this next test.